Well, this is a really great opportunity, and the previous talks were great and talked about some themes that echo very much for me. We talked about human-robot collaboration or human-AI collaboration. We talked about what AI is and what AI isn't, and the importance of when you have a hardware company knowing what not to build and listening to your customers. So those all sound like really good ideas. So I would like to talk a bit about those industrial robots, industrial automation. Just to start with, how many people here have been inside a car factory? It's pretty cool, huh? So industrial robots, these are just incredible machines. And they have capabilities way beyond those of the human body. And they can lift 200 kilograms, move it 4 meters at 2 meters per second, and place it precisely with sub-millimeter tolerances. And if anyone here has built hardware and knows about reliability, they can do this over 100,000 hours of continuous operation. And if your car has 100,000 miles on it, you've probably driven it less than 6,000 hours. So 100,000 hours. But I gotta say that the main thing that you learn from 20 years spent building robots is that people are amazing. Any people that we can do what we consider to be, low-skilled labor, and we have capabilities that are far beyond what any robot can do today or for a long time. And what this means is that while this is what a lot of us imagine when we think of, heavy industry and manufacturing, that the reality often looks a lot more like this. That there are some tasks that can be and have been fully automated, but the vast majority of the operations that go on in a factory today are done by people. So I want to talk a little bit about, why this is. And what it often comes down to is that building robots is a lot harder than a lot of us think. One thing I've noticed is that when you talk to, for example, let's take a topic like cybersecurity. In my experience, the more somebody knows about cybersecurity, the more worried they are. The more somebody knows about robotics, the less worried they are. I have never met a manufacturing engineer who's worried about the robots taking over the world. Because building robots is just a lot harder than we think it is. In particular, building robots that can do multiple things in multiple environments. It's really hard to build a robot that does one thing in one environment. And that's what the vast majority of industrial automation looks like today. They are purpose-built machines that do a single operation. And, we're all used to seeing exponentials that make us happy, right? Everything gets exponentially better. We have Moore's Law, and everything will be great. We do just this one thing, and then, we'll be all set. In robotics, the exponential goes the other way around. It becomes exponentially, and I really mean exponentially, not linearly, harder to build a robot that can do multiple tasks in a variable environment the way every single one of us can do. My favorite example, I come up with examples of stuff robots can't do. My latest one is cardboard boxes. So just about any person, even someone who's really not too bright, armed with, a box cutter, can open any cardboard box that comes to your house of any shape, any size, with any kind of tape, any kind of fastening. You can open it no matter what's in it, whether it's the packing peanuts or, plastic bags or whatever. You can fiddle through all that. You can find the thing inside, and you can put that thing on a flat surface. There is not a robot in the universe that can do that. And there's your incoming receiving for your manufacturing line is, opening cardboard boxes. So talk a little bit more about, robots and robots are hard. I'm going to go back to the beginning of my career in robotics as a 19-year-old math major who didn't know anything about software, anything about robots or any of this stuff. I got a job at a company called iRobot, although they had a different name back then. And I was there for about 7 years, and I learned a lot there. And two of the most important things I learned at iRobot were this thing about how hard it is to do the things that we do naturally. And this is a thing, we were talking about AI and how people used to think chess was AI, and I liked the almost implemented thing. The one I've heard most often is AI is whatever computers can't do yet. So all these things that we don't even think about as being hard end up being incredibly difficult for robots. And then you add to that the fact that if anyone's ever worked for a company that went through that, hey, we have a prototype, we're going to manufacture it soon, right? To, oh, we actually have a product and it's rolling off the line. That difference is immense, and it's especially immense in robotics. And because I started my engineering career in robotics, it took me a long time to figure out, what's actually unique to robotics about what I've been doing versus, what's general to everything. So one thing that's unique is robotics and closes the loop with the analog world. So what that means is that you're getting input from the real world, and your output affects the real world. So for example, you're going to write an algorithm that tells you what to do with your sensor data. Well, what does your sensor data look like if your sensor's on a mobile robot that reacts to the algorithm that you wrote to tell you what to do with your sensor data? It's essentially a chicken and egg problem. You don't know. And let's say you have this whole data set that you collected, right? Now you can iterate faster on your algorithms because you have this data. Well, now you change your algorithm, and in response to your new algorithm, the robot does something different now. So the data looks different now. So all of that recorded data is useless. So these facts combined come together to make the advice that I give to, baby roboticists today is, if you want to commercialize, build a robotic product, and you want to do that in, let's say, 2 or 3 years, you need to pick something that your average robotics grad student thinks they can build in 2 or 3 weeks. Because that's the difference in what it actually takes to get to a product that people can use. So what this means is that, robots there's so many things that we have that robots don't. We have flexibility, we have judgment, we have perception, we can adapt, we can change, we can learn. So the best application for robots have to be focused on the places where they outclass us. Robots can be stronger, robots can be faster, they can do a task over and over and over again without stopping. So right now, we're often used to today looking for ideas for technology. We want to say, people say, oh, the technology changes of the past, the most recent technology changes have happened and have affected us most in our homes and our offices. So we kind of look for applications there, build the app that you want to use. But the best applications for robotics are not in your home and they're not in your office. They're in places where serious physical manual labor gets done. So you have to go outside what you're used to, and you have to look beyond that. So when I started my first robotics company, a few of my colleagues, Joe Jones and Paul Sandin from iRobot, who were the guys who convinced iRobot to give them $10,000 in 2 weeks to build a first prototype of the Roomba. So they left and they asked me to join them in starting this new robotics company, and we went and looked for places where work was getting done. And we ended up building a materials handling robot for the nursery and greenhouse industry. And this is a robot that is out there today all over the country, moving plants. And we looked for, real work. This is the work that these robots are automating consists of bending over, picking up, 40 pounds worth of plants, walking 20 feet, bending down, putting it over again, and doing that all in the middle of a field in Alabama in July. This was good work for robots. It also met the criteria of, your robot grad student thinks they can build it in 3 weeks. It was a little robot that moved a potted plant from point A to point B. How hard could it possibly be? Of course, in an unstructured environment, in the real world, in all kinds of difficult circumstances, this is a big project. One of the things that allowed it to be possible, though, was that we didn't aim for 100% automation. In these kinds of unstructured environments, 100% automation would have been impossible, prohibitive. But we said, look, let's make it so that the robot can move 99 plants and the 100th plant can be moved by a person. So now you can have a person who, instead of bending over and moving plants all day, is now supervising a team of 8 robots. And that ability to have the system work with people was actually what made it possible to build that product today versus, 50 years in the future. So this was a really cool project, and I really loved it. It was also challenging. This was a market that was not used to adopting technology, that was slow to change, and that one of the things that we ran into that if any kind of, I think, industrial or B2B company may be dealing with is that if you have, your customer will say, oh yeah, we really like this thing and absolutely we'll pay $50,000 for it. But then when it comes time to spend that $50,000, you're dealing with a limited CapEx budget. And it's either buy these new robots or replace the Northwest greenhouse. And all those other criteria that you're dealing with make it really tough for them to necessarily commit to that new technology. Anyway, fast forward a few years. My co-founder, Patrick Silvalvaro, who I had consulted for years and years ago, was starting a new venture, this time in industrial automation. And this is a bit of a homecoming for the AI robotics world in that industrial robots were actually the first and really biggest to date success story of robotics. These companies came out of AI robotics research, back in the 70s and 80s that then led to the creation of all these, robot arms that are in factories today. And it turns out that one of the biggest trends in manufacturing right now is a move towards more flexibility. 5 minutes. Got it. So flexibility. So we have shorter product cycles. We have higher product mix. We have mass customization. All of these trends are pushing manufacturers to be more flexible. And what is the most flexible resource that you are always going to have in any manufacturing facility? Is people. Always. So these giant industrial robots, that very speed and strength that makes them so powerful becomes a huge limitation because it makes them dangerous. So literally in today's factories, robots are kept in cages. It's not to keep the robots in. It's to keep the people out so they don't get hurt. But what this means is that automation becomes an all or nothing proposition. You either need to automate the entire process or you need to automate none of it. And automating an entire process can be incredibly capital intensive, incredibly brittle, and inflexible. So often, if you have to make that choice, you don't automate at all. So the challenge that Veo has taken on is making those robots not smart enough to replace people because we don't have a spare 500 years. We are making robots just smart enough so that they can work safely with people. We can monitor a work cell, we can see the people working in that work cell, and we can override the robot trajectory so that it slows and stops and doesn't hurt a person. Again, there's that, can a grad student do it in 3 weeks criteria? Just see the person and stop. Pretty simple, but in a real life situation, it's incredibly complicated, and more so because it's a safety critical system. And this changes how you do engineering. And this has been one of the major things for me to learn. When I first thought about this topic, it was a little bit daunting. Do you want to build systems where, people's safety is on the line if you do it wrong? But what I thought about is that, robots were never going to actually, if we stuck to little robots that couldn't really do much, we were just never going to realize the potential of that technology. And so we decided to we learned from all of the places where people do safety critical work today. People in avionics, in automotive, in medical device. Our society has come up with, and there are standards for how you do engineering in safety critical applications. And so those are the practices that we are adopting to build this system that then allows people and robots to work together safely. And once you have that basic ability for people, a person and a robot to be in the same place, that opens up essentially an entire new field of possibilities for how you can do industrial processes. Robot carries big heavy thing, person attaches little fiddly connector. Person takes thing out of cardboard box, places it in the stand, robot performs careful operation with fine tolerances on the thing. And manufacturing engineers, who are the people that build these, our customers build factories. And people who build factories have entire engineering teams full of brilliant engineers who are working on essentially insanely complex Rube Goldberg contraptions that have to work every single time. And we're giving them a new tool to do that. And that opportunity has been just amazing, just to be able to be out there and working with those people. And it's been able to just, in summary, to basically crystallize and bring all of those ideas from all that time working with robots and starting robot companies and learning about what robots do well and what people do well, and really make that right at the forefront of what we're doing.
Thank you very much. What's the next frontier, I guess, in terms of...
I just realized I have a video I didn't play.
Okay.
Can I play it?
The time. Yeah, absolutely.
Actually, ooh, there's music. I didn't know there was music. So this is a KUKA robot, and this is a task that this robot would have been caged, and you would not have been able to have a person and a robot doing this together. When we bring in manufacturing engineers and they first see that, put up your hand and the robot stops, their jaws drop. This is what they've been looking for. And so we're monitoring, you can see up back in the screen there, we're monitoring the area around the robot. All of this fancy stuff, this is manufacturing engineering 101. This is not new. What's new is someone being able to walk up to that robot and that robot being aware of them and stopping for them. There we go.
And no production engineers were harmed in the making of this video?
No production engineers were harmed.
So what's the next frontier in terms of bringing AI to robotics? What are some of the things that are just starting to bubble up in research that are very exciting to you?
I think that there's a huge amount. So as I was saying, industrial automation was this sort of very early success story of robotics research, but then it's kind of, now it's like there's this Berlin Wall or something. It's this completely separate world, the world of industrial automation, the world of robotics research. And I think what we're seeing is that those things are actually starting to be able to look over the wall. So much of what robotics now does is about doing something in a very precisely fixed way, and all the programming is done manually, and it's quite cumbersome. And there's a lot of interesting ways in which robots being just a little bit smarter can loosen some of the constraints. For example, being able to pick something up that's not exactly where you thought it was. And being able to, modify things on the fly to be able to deal with variability, although you don't want to do that too much, because this is something I really discovered working in this industry, is that the thing we think of as a robot, like that robot in a factory is like a transistor on a circuit board. It's part of a much bigger, more complicated machine. And the people who build those bigger, more complicated machines, they don't really want that transistor to have a whole lot of free will. It really needs to do exactly what it's told every single time and not screw up. But there are these ways in which additional perception and intelligence can augment what the systems can do and essentially make, again, with that flexibility in mind, make it easier and more flexible to build advanced manufacturing systems.
Great. And how do you, how do you go to market as a robotics company? Do you sell software to KUKA? How does that work?
No, that's actually a great question. So the way the industrial automation industry works is that it's kind of the way, if you redo your kitchen, you have a contractor come in and they're going to build the whole kitchen, and they're going to buy a fridge from Electrolux, and they're going to buy the countertops from somebody else, and they're going to buy a sink from Kohler, and they're going to buy all these different pieces from all these different industries. They'll put it all together to build you a kitchen. So industrial automation works the same way. So there's a systems integrator, is what they're called, and they will buy a robot from KUKA, and they'll buy a camera system from Cognex, and they'll buy some safety PLCs from Pills, and they'll buy this system from Veo, and they'll put all that together to build a work cell for a customer.
Good. Very interesting. All right, bunch of questions.
Thanks. We have some investments in manufacturing. Your point about having the robots actually secured in some cases, could you speak a little bit about labor unions and their how are they adopting to this? Are you involved in some of those negotiations or advisory there?
So we haven't been involved with any negotiations unions per se. With the concept of safety in general, this industry has a very, very good safety record. Job displacement. So again, what we usually find is what we are doing is we are not displacing labor. We are actually enhancing productivity, allowing for people and robots to work together better. So in general, what we find our manufacturing customers are very much they want to build faster factories that can make more things. And this is a way of making more things with more people.
Throw it, yes.
Thank you, very interesting talk. I do have a question regarding the algorithms that you use or plan to use. How do you quantify safety? So what's a good strategy? What would you be looking for? Can you just put in the neural net and hope for the best? Or
yeah and no, you cannot. And that's actually, we are not using any machine learning in our algorithms. We are using deterministic computer vision techniques for exactly that reason. In fact, the standards explicitly recommend that you not use machine learning in these applications. There's a lot of interesting topics and implications to that, especially when it comes to autonomous vehicles. But we have worked on essentially scaling back what's required of our system so for example, we don't definitively identify people. We don't say that's a person, that's what they're doing. We just say, because in an industrial work cell, you know what's supposed to be there. We know what's the work cell, we know what's the robot, and any intrusion of sufficient scale into that work cell that we can't identify deterministically as part of the work cell, we say, well, we're going to treat that as a person. So we always are making these conservative assumptions. We monitor all of the occlusions in the space. So we don't even say, oh, we're just going to react to what we see. We will, in fact, react to anything that we cannot verify is empty with our sensors. Sorry, I can't hear you. Yep. So we are programming in C++, but you have to use a limited subset of C++. And there are standards that 61508 is the functional safety standard that lays out requirements for programming languages, for programming practices, and we are designing the system for compliance with those standards.
I do. Thank you for sharing, and want to know if there's any recommended reading or just anything that you relied on as a book when you were beginning this whole foray into robotics. What would you recommend as a favorite book, something to get?
Oh God, someone was asking me about this just the other day, and I don't have an answer. My programming career, like the first book that was actually a significant thing to me was on Lisp, because I was at iRobot and we all came out of the iLab and all that code was written in Lisp in the first early days. But everything else I just, picked up on the job. For this industry, you can read about things like, Toyota production system and modern manufacturing. But robotics, I don't have a good answer.
All right. On this note, thank you so much. This was terrific. Really enjoyed it. Thank you.